Yeah, thank you, Joanna. Hello, everyone. Welcome to my talk on why our world is unreal. I have to give a little bit of a disclaimer that this title is actually a bit misleading, so it's actually not completely correct. So the correct title should have been Why Our World is Unreal and or Non-Local. And if you don't know what I'm talking about, I hope by the end of the talk you will, and things will be a bit clearer, especially those people who are not from the physics kind of background. But really, it's going to be a talk about basically some physicists rambling about special relativity and quantum mechanics. And feel free to interrupt at any point and just ask if you don't understand something. It is a bit of a mind-breaking topic, I think. At least I had to take some breaks while writing this up, just because it's just sometimes makes you think a bit, think you're going insane. Also, this is not actually this is not something I do for my PhD right now. It's something I did I worked on an experiment which I'll present later during my bachelor's thesis. So I have a sort of relation to this topic, but also I'm not an expert. Let's say it like that. Okay, but before we kind of delve into why this is the case, we have to start with a little bit of background. So we'll have to talk about a bit of quantum mechanics. And so quantum mechanics in a nutshell is you have a particle like that. We'll see that particle pop up around the place a few times. And quantum mechanics tells us that the particle is described fully by this wave function, psi, which is just a mathematical description of the particle. And it contains all the knowledge we can have about the particle, according to quantum mechanics. And so, but even though if we know this psi fully, we can only make statistical predictions about experiments in reality. So say I know psi, I know I can make a prediction that I'll measure my particle with 50% of my particles will end up here and 50% will end up here. But it can't tell you that particle which I'm sending out right now will end up here. That's just impossible. This is something that quantum mechanics kind of has built into it, and it seems to describe our nature quite well. But yeah, it's important that these predictions really are only statistical. And another bit of quantum mechanics we'll need is from that guy. That's Werner Heisenberg. And he has a famous theorem named after him, Heisenberg's theorem, which is usually in terms of position and momentum, but really it can be any sorts of different variables. And what it says is that there are certain observable quantities that we can't observe at the same time, and actually that they don't exist at the same time. So as I say there are certain things you can't know simultaneously. So the famous example is position and momentum. If you measure the position of a particle, its momentum will be totally undefined. And at the same time, if you measure the momentum of a particle, its position is basically undefined, which means that kind of the concept of position and momentum, they kind of can't exist at the same time. They can't be real at the same time. We'll delve later into under which definition they are not real at the same time. But you have to keep that in mind, basically, that these so-called canonical conjugate variables don't have physical reality at the same time. And another consequence of Heisenberg's theorem is, well, if I measure something and something else changes, well, then my measurement surely has to influence what I'm measuring. So measurements will, in the end, change our system. So say I measure the momentum, then the position is undefined. And so I've changed that particle. Okay, the last bit of quantum mechanics we'll need is going to be entanglement. And I've done a little sketch thing about entanglement. So because people always make it out to be really complicated, but it's actually not that complicated. So if I robbed a referee and stole his red and yellow card, and I just put them into envelopes. So just put them in there, and then and I'm a forgetful person. Can't remember what I put in which envelope. So what do? I just look into one of the envelopes and see, okay, that one contains the red card. So obviously the other envelope has to contain the yellow card, right? So there's no real mystery behind that. It's really easy. Now, if I rob the referee, but I'm blind and I need my good friend to tell me which card is which, again, I take the two cards, but I can't tell which one is which. But I know one of them will have to be yellow and one of them will have to be red, right? Because it's a referee. It's what they do. So again, I put them in these envelopes, and now I don't know which one I put which card, but still, one of them has to be red, one of them has to be yellow. And if I check one envelope again, okay, I see that one's red. So again, in the other one, there has to be a yellow card. So this is kind of the concept of entanglement. You have sort of a set of two ways. So obviously, the card in that envelope could have easily also been the yellow one, and then I would have known the other one is the red one. So in that sense, like if I know something about one envelope, I know something about the other envelope. And the same is true about particles. So even particles can be in these kind of entangled states. So I can kind of make them interact in such a way that one of them has one property and the other particle has, for instance, the same property but in the opposite direction. So an example of this would be magnetic moment. So one particle could have its magnetic moment pointing upwards and one downwards, but I don't know which one is which. And so again, they can be in this entangled state. I can put them in my envelopes, separate them again, and have a look at them. And if I know, okay, that particle had magnetic moment pointing downwards, then the other particle must have had the magnetic moment pointing upwards. A little bit of a weird thing in quantum mechanics is that, well, with the referee cards, we would have said, okay, they are red and yellow. Here, until you measure it, because of this weird canonical conjugate variable thing, the particle actually is in a so-called superposition of the two states. So it is actually both up and downwards pointing at that moment. And only once you've measured it do you know it's in this state. And this kind of weirdness, once you've completely understood it, which took quite a while actually, you realize that this can lead to a paradox. And this paradox is named after these three guys, one of which you probably know, Albert Einstein. The other ones are Podolsky and Rosen. And they came up with this famous EPR paradox, EPR, Einstein, Podolsky, Rosen paradox. And before we can fully understand it, we have to go through their definitions of what is real and what is local. So I took here the definition they actually have in their paper. The paper is, by the way, I think you can definitely access it with Cambridge. And it's a little bit physicsy, of course, but it's actually a really nice read. It's called Can the Quantum Theory of Nature Be Considered Complete, I think. And it's a really good read. But yeah, they say, okay, what is real? Well, they say a sufficient condition for the reality of a physical quantity, say its momentum or something, is the possibility of predicting it with certainty without disturbing the system. So the really important part here is there's two important parts. There's the certainty, so I can definitely say which quantity I will measure, and without disturbing the system, so I don't have to measure it to know it, so to speak. And another thing they needed for their paradox is the concept of locality. So locality is kind of what Einstein is quite famous for. It's the idea that sort of things can only interact with each other with a finite speed, which he called the speed of, which was the speed of light. So in that sense, yes, particles that are very far apart can't immediately interact with each other. But they now realize that these two concepts and the bit of quantum mechanics that came beforehand lead to a paradox. So let's walk you through this paradox. Okay, let's say we have our two particles again. They're again in this entangled state. Now, again, I don't know which one has which quantity. And so I put them in my envelopes, and this time I put these envelopes really, really far apart. So they're so far apart that no light can travel from one envelope to the other envelope, which means they're basically separate subsystems that can't interact with each other, according to this locality principle, right? But now they thought, okay, well, I can measure something on that right particle and then infer information on the left particle. So say, for instance, I measure the momentum in the z direction, so pointing upwards or downwards. And I see, okay, that one would be downwards. Then surely the other particle must have momentum pointing upwards. But I could have just as easily chosen to measure the canonical conjugate variable. So I could have just as easily measured the magnetic moment, for instance, in the x direction, which is, according to Heisenberg, not possible. You can't do simultaneous, you can't do measurements of canonical conjugate variables or prediction of canonical conjugate variables at the same time. So I could have measured the z direction and inferred information on the left particle without disturbing the system because they're separate. So that must mean that the magnetic moment in the z direction must have physical reality according to this definition. I can predict it with certainty without disturbing the system because I'm only measuring the other system. But I could have easily done it in this direction. Again, would have had with certainty information about the other system, which I didn't measure. I didn't predict anything. So this is the paradox, right? This is obviously in contradiction with what Heisenberg said, that these two canonical conjugate variables can't have simultaneous physical reality. They can't exist at the same time. And so what Podolsky, Podolsky, Rosen, and Einstein came up with is something called, well, they didn't call it that at the time, but it's something called a hidden variable theory. So that theory says, basically, we don't know everything. This notion I said before, if we know the wave function, we know everything. It's kind of not complete, but there is hidden information that we don't know how to access, but that predicts with certainty the outcome of these measurements. And that obviously would then clear up the paradox, because then both of these variables do have simultaneous physical reality. So yeah, their conclusion was quantum theory must be not complete. There must be something missing, and we need an extension form of these hidden variables. This was back in I think this paper was published in the 30s, and people were then kind of, okay, well, we have no idea if this is even measurable, or like, what can we do with this? And it took till basically to the 1960s till someone came along and thought about this problem again and actually realized that this has some severe consequences on measurable things that we can observe. And that person was John Bell, this guy, and he basically realized that there's a measurable difference between these hidden variables theories and quantum mechanics, and that we can, in experiment, measure different outcomes if we had the one theory or the other theory. I won't go into the details of how Bell's theorem works because it's just lots of math and really not that interesting. But I've included one small equation. Well, it's not even an equation, it's an inequality, really. It's called Bell's inequality. Well, actually, that's called the CHSH inequality, but don't worry about that. It's kind of a derivative of Bell's inequality. That says that this measurable quantity S, which has to do with coincidences of photons or entangled particles, that is, for a hidden variables theory, less than 2. Whereas for quantum mechanics, it would be around 2 times root 2, or a little bit less than that. But definitely above, it can be above 2 for quantum mechanics, but has to be less than 2 for a hidden variables theory. And that's going to be really important. So, so Bell found this thing, and now everybody was kind of trying to measure this. And important persons in this measurement, like trying to measure this, was, for instance, Alain Aspect in France. Later it was Erwin Zeilinger in, I think, in Vienna or somewhere in Austria. But the experiment I worked on, which was actually quite late, so they only published in 2017, was in Munich. And, well, we basically just measured this S parameter and had a look, does it actually violate Bell's inequalities? So how do you measure this kind of thing? Well, it's actually not as simple as people would think it is. I'll walk you through this. I'll try to walk you through this. The idea is that you have something called an event-ready measurement. So you have to first produce these entangled particles, right? And the way you do that is, well, first of all, let's start with an atom. An atom has like certain levels at which it can be. Kind of like if you know Bohr's atomic model, where you have these kind of shells. It's somehow similar to that, basically. In this case, so you can kind of excite the atom from its original ground state to excited state, so to an outer shell basically. And then the atom can decay. And it can decay, this is, by the way, is rubidium-87. It can decay in two ways. It can decay either by producing a photon that rotates into the left, it's called left circularly polarized, so it's rotating like this, or a right circularly polarized light, which rotates like this. And depending on which light it emits, it ends up in a different ground state again. So as you can see here quite clearly, if you emit the photon with the L, you get into the ground state, which has the magnetic moment pointing downwards. Whereas if you do it with the R, so with the right polarized light, you end up in the ground state with a magnetic moment pointing upwards. So in that sense, we have the same outcome as we had before. We have information that if we measure the polarization of the photon, we can infer information about the atom. And at the same time, if we measured the atom, we could infer information about the photon. Now, for reasons that I'll explain later, they did this twice. So we actually have these two atoms in two different traps. So one is down here and one is down here. And so we have two of these atoms. But we do the same with both of them. So we produce we produce two photons, or two pairs of entangled atom-photon pairs. And then we collect the photon, and well, because they have to be space-like separate, so they have to be able to prove this non-locality, they have to be very far apart. We send the photons through a long single-mode optical fiber, and then we do something called, well, it's now called a Bell measurement, obviously because of John Bell, sorry, not Graham. And what that does, it's quite crazy. It can it's something called heralded entanglement. So the photons, you do a special type of measurement on the two photons, which is done basically here. And that kind of measurement switches the entanglement between the photons and the atoms to between the atoms. So after you've done this measurement, which is a special type of measurement, you end up with two entangled atoms. So you end up with basically what I explained earlier, with these two atoms that could be either pointing upwards or downwards or upwards and upwards. So their magnetic moments are entangled. And well, this is really what we wanted, because now we have two entangled atoms that are space-like separated, so two particles that are space-like separate, which is what we want to measure the Bell inequality. And now the only thing we need to do is basically measure them. So that's why this is called, was called in the paper an event-ready measurement, or an event-ready test, because basically, unless you've done all the preparation and got the right measurement here, you wouldn't measure. You don't even measure, and that is important later, because all of this is kind of took so long because it has to close a lot of loopholes, which I'll explain later. And yeah, so you end up having these two entangled atoms. You measure their magnetic moment separately at well, to measure this S parameter, you have to measure at random bases and at random angles, and then you look at the correlations between the measurements. And well, they did that and calculated this S parameter of 2.221 plus or minus 0.033. So several sigma violation of Bell's inequality. This means that certainly something with hidden variables is probably amiss. Like, this is a strong indication, and this is not the only indication. It's one of many measurements that all measurements so far have basically violated Bell's inequality. And this is really strong evidence that this hidden variables theory can't be the answer. A quick note on this type of measurement. It took so long to do them really well because this one is considered a loophole-free measurement. So these measurements date back to the 70s and 80s, basically. But what they had were so-called loopholes. So, for instance, there's the locality loophole, which basically means, well, you measure your two entangled particles, but they can easily interact with each other because they're really close to each other, or your measurement process just takes really long. But that was closed in this case because we had this measurement of the atomic magnetic moments, which is a measurement we can do really, really fast. So it takes a couple of nanoseconds. And so this loophole was closed, and also because we had this event-ready test. Then another thing you have is this sampling loophole. So the idea behind that is, well, if you have a detector that only detects like every 100th photon or something, then what can happen is you could just measure those photons that kind of accidentally violate Bell's inequality. So kind of you're just looking at a subset of what is actually what's actually happening. And so to close that, we had to basically make sure that every measurement that we do gives us a result, and we don't sort of miss anything. And this was done in this case by having this event-ready preparation. So we only measured when when we measured these photon coincidences. So when we knew that the two atoms were entangled, which means, and then we always get a result because these atom measurements are actually really precise. So the sampling loophole is a problem specifically when you do it with photons. But yeah, so this was done here because we have this event-ready preparation. And finally, something that is kind of the most abstract of the three is the free choice loophole. So as I said earlier, you kind of have to measure at random bases these two atoms. So you kind of have to choose either an angle like this or an angle like this to which two you want to measure them. And the way they did it in the experiment the first time was they had a random number generator which worked on quantum mechanics. So kind of it's a bit contradictory that you try to disprove the principles of quantum mechanics by using quantum mechanics. So what they did was they used an experiment where basically they had 100,000 participants clicking 1 or 2, and then that would correlate to measurement bases in which them and some other of these experiments chose their measurement basis. So it was literally the idea that what is completely unbiased, and that's like we came up with the free choice of humans. Another thing they did was actually to use this was only on a very recent paper, is to use the light of distant quasars that has traveled through the universe for like a couple of million years, because they wanted to make sure that the light didn't somehow send information beforehand to the atoms to tell them which measurement outcome they should give in the end. And so, I told you, it's a bit crazy, but like at the same time, it's really interesting that these loopholes exist and that we kind of address them one by one. Okay, back to is our world now real or not, or what's happening? Well, basically what I've just shown is that these local realist theories, the one that are these hidden variable theories, local hidden variable theories to be precise, they can't work. They're obviously not in congruence with what we measure, and they contradict our experiments. So as a physicist, we kind of have to say they are probably not correct. So we have to give up either the concept of realism or of locality, which means we either have to accept that things don't have defined values, like momentum and position aren't defined values if we're not watching, or we have to accept that things travel faster than the speed of light and kind of interact faster than the speed of light. I've put here some examples of different theories. So technically there's still one local realist theory that could work out. It's called superdeterminism, and it would basically mean since the Big Bang everything has been determined and you can't influence it whichever way you like, which is kind of a bit depressing because it means like free will doesn't exist and these kind of things because everything's already decided. So yeah, people kind of don't like that one. For a local non-realist theory, I couldn't come up with any, to be honest. I didn't really look into it that far, but I didn't get one from the top of my head. A famous realist non-local theory, so a theory where things like position and momentum are still defined at every time and like always, is for instance Bohmian mechanics, where you have something called a guiding wave, which kind of influences the path particles take. So you can, for instance, recreate the famous Young's double slit experiment with Bohmian mechanics without big issues. But the thing about Bohmian mechanics is that this guiding wave has to be non-local. So yeah, you have to basically give up that things cannot interact with the speed with like a boundary of the speed of light. And then we have the non-local and non-realist theory, which is quantum mechanics, where you have these strange interactions at a distance, and you have these things not really existing until you measure them. And but still, like, we still have the problem that Einstein, Podolsky, and Rosen put up, right? We still haven't addressed that issue. But actually, people have kind of thought about it a bit harder and realized it's actually not that big an issue. So, we've ruled out hidden variables, and we don't get a paradox if quantum mechanics is non-local. So if there are these, if just particles can interact with each other non-locally. And the important bit people realize is that this non-locality doesn't coincide with non-causality, or it doesn't break the laws of special relativity. So I'll explain what I mean by that. So we have non-locality, meaning particles don't interact at a distance, and we have causality, which means one thing makes change, or one thing causes another thing to happen. So if we can start off with these entangled particles, Alice and Bob. So these are now two particles, and we have our two experimentalists, Alice and Bob, and they're in different labs. They're space-like separate, and they decide to measure their particles. Alice starts measuring her particle. She has a 50-50 chance of measuring either up or down. Okay, fair enough. But at the same time, Bob also has the same chance. So if either of them starts measuring and then the other one measures, they all get the same result. But even if Alice first measures, Bob will still have a 50-50 chance of measuring either the one thing or the other thing. Only Alice knows which outcome Bob will measure. And so that information is kind of still contained on the left-hand side, whereas Bob can basically and will measure up or down. And especially if he does like multiple measurements, he will see in his statistics that it was 50% up, 50% down. And Alice will see she had 50% up, 50% down. And only when they come together will they see that it is perfectly anti-correlated. And so Alice, cannot really influence anything that Bob does. So because she can't influence the measurement is still completely random. And Bob, because of this, can also not get any information out of the outcome that Alice has. So there's no chance of producing like a communication link. Like Bob can't even tell if Alice has measured at all. So this means that these results are still completely random, and there's no way of transmitting information or anything like that. And this means, there's no information exchange. Okay, to finish this whole talk off, I've got a little comic basically saying, well, in the end, nothing really travels as fast as common human misunderstandings. And thank you, everyone, for your attention. Yeah.